in this section is called the factors that affect solubility. And then we'll review, not much to review, I feel like. Super easy, everything. Oh, I'm done too. It's May. Might as well be May. Okay. So here we go. You did great.
I did good.
If you got above a 20, you did great, especially if it was your first time. We can't all be perfect Sorayas. All right, here we go. The common ion effect. Look at the screen.
Okay, I'm sorry. I just didn't know. Sorry, 34.
Yeah, I don't know.
I'll be done.
Yeah, I'm done.
Okay, leave the room, please. Okay. The common ion effect. If one of the ions in a solution equilibrium is already dissolved in the solution, the equilibrium will shift to the left and the solubility of the salt will decrease. So look right here. If I want this to dissolve, but I put it in a solution of Na2SO4, which does dissolve, I already have SO4 minus 2 here. So if there's already some of this in there, Le Chatelier's principle says I would go away. So the solubility, listen to this part, the solubility of a substance is negatively affected by the presence of a common ion. It will decrease. It kind of makes sense. Like if you need room to put SO4s, but that room's already taken up, then they don't break apart. They have to stay together. Yep, or I can add it later. If I have this BaSO4 already dissolved, so I have some Ba plus 2 and some SO4 minus 2, and it's at equilibrium, and then I drop in Na2SO4. This is extremely soluble, so it breaks apart pretty easy. That means there's now a ton of SO4 everywhere. So there's not enough room. So what it does is it forces the Ba to attach to BaSO4 and becomes a precipitate at the bottom. So if we have a common ion, the solubility of the substance decreases. That's all you really need to know. This is Ba, that's supposed to be Na. This supplies the common ion right here. But this was the solution that was there in the first place. Yep, the equilibrium will push towards the left or towards the, oh, hey, the BaSO4 part. Hold on. I'm fixing what I just undid. This board is on a piece of metal and it vibrates a ton, but behind the piece of metal, I have a board that makes it push the metal out, so it's a little bit more stiff. When I pulled this, I'll do it again. The board fell down in the back. It's okay, Bennett. Everyone's still alive. All right. Oh, that was stupid, Tom. It's too far to reach. I'll live. See that? But if I don't have it, it wobbles a ton. So. There you go. Everything you always wanted to know about Davidson's board. Okay, next up. All right, pH. This one's a little bit trickier, but not bad. pH. If a substance has a basic anion, it will be more soluble in an acidic solution. So, what do we have here? So if I don't know, they have magnesium hydroxide. It's really hard to see, but inside here is magnesium hydroxide. And it will dissociate. Just gonna put an arrow like this, you all right with that? 2OH minus. This is all about Le Chatelier's principle. We come back to it very often. If you have your solution and you want to dissolve this in it, the things that you can do to make this side be formed instead of that side is I can remove OH minus. If I take away OH minus, more of this breaks apart, because if I take away, I stay. Does that sound familiar? Okay, one way to take it away is to have H plus in the solution. Right, if I have H plus around, well, then those two bond to form water, which means the concentration of OH just went down. So another one of these will pop off, which means the solubility increases. Yep, the solubility would decrease if I had a basic solution, yes. Decrease means less soluble. No, that's okay. She asked the other direction. That's why it got confusing.
Oh, okay.
So it becomes more soluble, or its solubility increases in a basic, or sorry, acidic. But then she said, oh, so it's the other way around, basically, which was right. Okay. So when you have a question like this, just try to remember Le Chatelier's principle. If we add or take away, the solubility of the solid will be affected. All right, so here, substances with acidic cation are more soluble in basic solutions. So just the same idea. All right, complex ions are no longer tested on the AP test, which is a lifesaver because they are weird and hard, especially naming them. Oh my, that's been a long time. You don't need that. But a complex ion is something unique. So usually we have Ag plus, and that's an ion. The complex ion is when the Ag plus reacts as well with NH3, and you get two of them. And then you have this complex ion. It's silver ammonium. It'd be like silver diammonia something, whatever it was with. They're super weird. But this is just another way of saying, hey, the solubility of Ag plus will increase if I have something that it will bond with. That's all it's really saying. But it throws in these things that are weird, like COSCN4. But it's just another way we're affecting the concentration, just like the H bonded with the OH to form water. The silver would bond with the ammonium to form that complex ion. So I wouldn't worry about those. All right, amphoterism. It's not something we talk too much about, but amphoteric metal oxides and hydroxides are soluble in strong acid or base because they can act either as acids or bases. So like it can go either way, accept or donate, but we don't usually, as far as solubility, we don't worry too much about this. But examples of such cations are Al plus 3, Zn plus 2, and Sn plus 2. I wouldn't worry a ton about this because once again, they're forming complex ions. So aluminum, it turns into AlH2O6. So aluminum hexa, that's not water, I don't remember what they call it. And then there's this one, aluminum dihexa, if I remember right. I haven't named them in 3 or 4, actually since 2013, 8 years. That's a skill that's gone from me. I will read you some names just for your pure entertainment. Because this is where you just thank your lucky stars. You are the H that you are. Well, there we go. So tetrachlorochromum 3. Sodium tetrahydroxyl That's NaAlOH4. That's good. Trans-chloro-bis ethyl-diamine hydroxycobalt 3. I'm not making those up. Those are real names.
Imagine getting that in a spelling bee.
Yeah, you're like, can you put it in a sentence, please? You're like,
Oregon.
actually, I
Yeah.
cannot.
You just put this, and then that.
All right, so here we go. Will a precipitate form in a solution? And this is related to what we just did. In a solution, if Q equals KSP, the system is at equilibrium and the solution is saturated. This sounds sort of like chapter 15.
Yeah, it does.
Chapter 15 was the easy. It was like the first step of a,
It's hard. The hardest part about these things is like retaining it.
yeah. What helps me retaining it is stealing someone's starburst. That's the, okay. Yeah, where's the yellow?
I don't know. It's good.
It's the best flavor.
You like yellow is the best.
It's tropical. It's tropical. It's the pineapple.
You like yellow normal?
No,
Okay, good.
but I'm a dad, so that's all I ever eat.
You like pink? You like pink normal?
Yeah, we get all reds now.
Why is yellow?
I don't eat orange. Makes me sick. Oh, I'm gonna spit. Don't make me talk. Yeah, when I was in junior high, we did that on purpose. Then you get in trouble. Okay, don't spit. I haven't tried since I was 12. Okay, here we go. If Q is less than KSP, more solid will dissolve until Q equals KSP. If Q is greater than KSP, the salt will precipitate until Q equals KSP. Now, I don't love how this is written. Anyone know why? What did I tell you to do with Q and K? Put them in alphabetical order. If you put them in alphabetical order, why did we do that? Then the greater and less than sign points where it should go. So these are true statements. Q is the KSP value at a certain condition and time. So I give you the values, you plug it in and calculate it, and then compare it to K. Hold on, what? We wouldn't relate these to temperature, because then that's whole math we haven't really studied. But I would say, all right, I have a solution that has a concentration of Ag plus equal to 1.3 times 10 to the negative 8. Cl minus, I'm not done yet. And it equals 2.6 times 10 to the negative 7. And so that it tells you you have those. So you would find the KSP. So you would just plug those both in. You'd multiply them by each other, right? Sorry, you would find Q. So someone do that for me real fast. That's a negative 7. So it will give you conditions that you plug in. Wow, that was a really small number. But I mean, that's the way I wrote it, so expected. So this would be the Q value because it's the condition I gave you. The problem would give you the KSP. It'd say the KSP for aluminum, or sorry, silver chloride is equal, let's say 2.6 times 10 to the negative 12. So then you'd line it up. We go alphabetical order. I have my K and I have my Q. Of these two values, which one's bigger? K is. So K is greater than Q, which means if I add more, I will form more of the ions and less of the solid. It will go towards the products. So would a precipitate be formed? The answer is no. In order for precipitate to be formed, we have to be forming the solid. This math is telling me I'm forming the ions. That's the quietest blank stares I've had in months. That's not a good thing. I've taught long enough to know that's let's just get it over with, Davidson.
I thought you were complimenting us.
Nope, that was my, I'm not putting you down either. It was my, I don't think anyone understood what I just did. Who understood what I just did?
Oh,
So I have one question.
I used to put it in practice.
Okay, hold on, you first.
So AgCl is then combined and then that's separated?
Yeah, I didn't, this is terrible because I never wrote it out. The problem would say, it would give you this. And then it'd say the KSP equals whatever that number was I made up there. It would give you the equation, it would give you the KSP, and it would tell you what was in the beaker. You had that much and that much. It wants to know if from that exact moment, will it make more ions or will it make a precipitate, which means more solid? Since our arrow pointed to the right, that means we make more of these and less of that. It sure can be. It can be on either one of my tests. I'll tell you what, to your benefit though, is about 10 minutes after this class is over, I'm getting on a track bus. I won't be home till late tonight. And then I have a different meeting of different situations later. And then I wake up in the morning and I'm gotta give you a test. So whatever I've already written is probably what's on the test. Yes.
So I don't want to like.
No. Hold on. I gotta just write a gigantic note. Okay. This thing. Okay, review. We already did this one, didn't we? We already did this one. Okay, now. No, they're like mango. How do you not know your Starburst by now? You're 17. Cassava melon. Part C. We did every part of this except for part C.
Oh, yeah.
So part C, you have this in your notes somewhere. It said a solid NaI is added to the saturated solution of PbI2. Assuming the volume does not change. They'll always say that just because there'll be someone like Tolman that's extremely detail oriented and be like, well, the volume went up because we got well, it says it did it. Okay, so here we go. That's not a put down, by the way. Okay, so assuming the volume doesn't change, does the molar concentration of Pb2 in the solution increase, decrease, or remain the same? Tell your partner real fast.
Right.
Okay, are we ready? Give me, is it going to go up, down, or stay the same? Okay, good. The answer is down. Pb plus 2 goes down because the addition of a common ion decreases the solubility of the salt. That's all you have to say. The presence of a common ion decreases the solubility of the salt. I said it so good. The presence of a common ion decreases the solubility of the salt. Oh, that was tough. Thank you. A. Yes.
So if I put down by increasing the I minus.
That's fine.
That works.
Well, put the word solid at the end, and then you're,
Make more PbI2 solid.
there you go.
Okay.
Okay. Do you remember how we did this problem? It was very simple. Because you're going to see it again. It'll be different a little, but not much. I know we did. That's why I said we did it 3 times. What?
Is the concentration of the eye just the same as the PV was?
No,
Oh, it kind of makes the difference.
2 times.
That's what it was.
Okay, here we go. Next. We done. Okay, let me see. Two. One of them I don't give you a test. Oh, generations of students have survived without a daily recording posted. It's only this year. You'll be fine. Okay. I'm not going to do the math. We've done that problem many times. You find the 2 values. You calculate the amount of acid based on the smaller of the 2 values. The difference is the amount of conjugate base. And then you Henderson-Hasselbalch. Okay. The pH made by mixing nitric acid. This is a strong acid. And NaCN. We've never done one exactly like this, but it doesn't really matter if it matches at all. I guess we have, sorry, it's just like this one. So we would just look, and I have 1 of 0.2, 2 of 0.1. So they're the same. Ooh, what does that mean? It means it's just a weak acid. And that Ka is our x squared over initial. And remember that x is equal to H plus. If you do the math and all it does is make weak acid, then to find the pH, you have Ka for HCN. Most kids that get this wrong tomorrow, they use the Ka for this, but that's not the acid made. That's the acid put in to make the real acid. So you have 2.18 instead of 5, whatever, who cares? Times 10 to the negative 6 equals x squared. Your initial is the total that you made, which they were both 0.2, right? Moles and moles. All right. So it's just 0.2 that you produced. Solve for x, negative log it, and you're off to the races. All right. This is going. What? This one? Okay, because what are these 2 words right here? Not 2 words, they're acids and pH. KSP is when we take a solid and dissolve it. Ka is what we do with acids. Kb is what we do with bases. Okay, here we go. The pH of a solution. This is just a standard, super not hard buffer, I hope. The pH of a solution made by mixing that much acetic acid and that much potassium acetate. What would the pH be? Oh, this is kind of dumb. So this would be like 1, 2, 3, whatever. It's numbered stupid, but like this is a question, this is a question, and this is a question. So how do we calculate the pH of a buffer? Finally, it's what you like. It's the Henderson-Hasselbalch. pH is equal to the negative log of the Ka plus the log of B, that's the acetate. So 0.3, you okay with that number? 1 times 0.3 over acid, which is the one that says acid. 2.5 times 2 is 0.5. And then we're ready to roll. What does that equal? 4.5? Sounds perfect. Okay, what would the pH be after the addition of NaOH? So I'm adding what? Acid or base? I'm adding a base. So my base will go up equal to the moles base added. My acid goes down equal to the moles base added. We've done this one at least 10 times. Not this exact same problem, but we take the same equation and all that changes is this ratio, right? So it's 0.2 times 0.1 is 0.02, right? All right, so which one goes up? Base, and that would go to 0.48, right? And then you do the same thing right down here. Hopefully you're very comfortable with those. All right, KSP. You haven't hated these yet. You probably already have it memorized. If it's a 1 to 2 thing, what am I going to use? All right, the KSP equals 4x cubed. All right, the only difference on this one is what? It's in grams, but it's April. You should be able to convert grams to moles. So you'd find magnesium fluoride 62. 62? Okay. So you take 0.00741 divided by 62, and that would give you your moles. All right. All right. It's in 100 milliliters. So that does matter, right? Because X equals a concentration. So I get this answer, and then I divide it by 0.1 liter to get the concentration. Then I'd be ready. What has anyone typed that in? $119? Okay. So then I do what to this? We okay with that? Okay, so that one was just a tiny sliver different because you had to put the grams to moles. And really, you had to get the concentration. Okay, this one might kill kids, but it shouldn't. You're going to think, wait, he's never taught me how to do it with 3 things, and especially if there's 4. Well, I know, but we didn't. You could, but you don't need to. This is Ca plus 2 and SO4 minus 2. Don't chop it into every single element. Remember, SO4 is its own thing. So this is just X squared. Like it's super easy, but some kids panic. They're like, to the 4th. I quit. All right. It's not. Just remember, that is actually just 2 things. One of them is a big thing, but it's still just 2 of them. So it wants KSP, and it gives you X. So you just square that. That's all you have to do. What? Yeah, it's really, really simple. Okay, well, the answer is already here. Which one of the following pairs, and it would be like A, B, C, D, E, cannot be mixed together, and it was already there, but it's when there's a strong acid and a strong base. You have to have something weak involved to be able to grab something. Both these completely dissociate. Oh, that doesn't fit very well. What change will be caused by the addition of a small amount of HCl to a solution containing fluoride ions and hydrogen fluoride? It will become slightly more. I'm adding, oh, hey, seizure time. I'm adding acid. So it becomes slightly more acidic, but not very much, because that is a buffered solution. It has hydrogen fluoride, so it has a weak acid, and it has the conjugate base. What? Yeah, these are multiple choice. I just cut off the answers. Okay. Which of the oh, that didn't have anything to do with it probably. Which of the following could be added to a solution of sodium acetate to produce a buffer? You're going to get this one super wrong. Because A is going to say H, C2H3O2, and you're going to be like, the easiest class ever. It's A, but no, it could be B. It could say HCl. It could be C, that's whatever. That could say HNO3, and B could say all the above, and you would choose D.
What does this have to be a strong acid?
It has to have a strong acid, or it can be a weak acid with its conjugate.
Oh, okay.
But tons of you will be like, nope, strong, strong, strong. It's obviously that, and that does make it. But remember, there's chemistry and there was secondary chemistry, which we did. All of these were the secondary chemistry, weren't they? Like what happens after the initial reaction. It could be. I don't know, Judah, because I haven't looked at it in 2 years. I really haven't. A 25 ml sample of the the unknown compound is okay. This one's a little tricky. You come over here. You find out the equivalence point is around 7, and then you'll take the pKa of each one of these, and the closest one to 7.2 is where you go. It's in the reading. We kind of went over it. It's all about the buffer range, and the equivalence point will tell you, if you take the negative log of everything, which one we're looking at. This is the same thing. You have this, you take the negative log of it and find out which one it's the closest to. We did it yesterday or the day before, I don't know. All right, this is not the answer, by the way. The molar solubility of blank is not affected by the pH of the solution. So did it say ALOH3? Okay, that one would be, because it has a basic anion, right? So you would need something that comes from both a strong or in a strong. So it was lithium and chloride. Does lithium form lithium hydroxide? No, it's tricky. This is a strong base, right? But remember, and I know it's stupid, that the definition of strong means they don't stick together. Lithium will stay separate from hydroxide. Chlorine is HCl, its counterpart, right? Which is strong, which means they don't stick together very well. So that salt is not affected by H plus or OH minus. Yep, and conjugate acids of strong bases. All right, my friends, there wasn't much more. Yep. You can watch. This last 10 seconds, you can watch it and you can see them.
Wait. Will you be able to come in during the time tomorrow?
Yeah.
Okay, nice. That's my plan. Ready?
Oh, that's a great one right there. Number 10. Nope, you got to read that one. You're welcome.
Jason, do you have Trevor's plates?
Derek has them. Does he need them?
Okay, so he doesn't need them. You just mentioned to me.
Yeah, sorry.
Tomorrow.
I forgot all about it.
Fine. Okay, thank you.
Yep.